Hi everyone, welcome to video 1.1.2. This is part 2 of our notes reviewing mole calculations. So now we're going to do some actual calculations, some stoichiometry calculations, just basic unit conversions here. Okay, so we have the number of grams, so we have a mass of CO2. And what we want to do is we want to find the volume. So we're going to go to liters in this case. So we're going to go from grams to liters, and you can't go directly from grams to liters when you're converting. If you learned something last year called Mole Island, you'll remember that you need to go from grams to moles, then to volume. If you didn't know that, you have to go to moles first. So you can't go directly from grams to volume. All right, so the first thing we're going to do when we're doing any unit conversions is to write down what we're starting with here. So I'm starting with 0.30 grams of CO2. And I'm going to go to moles. So to convert to moles from grams, I'm going to use my molar mass, which I always find on the periodic table. Quick review for how to find the molar mass if you don't remember. We have 1 carbon and 2 oxygens here, so you can pull up your periodic table and go ahead and look those elements up. We have 2 oxygens, so 16 times 2, plus 1 carbon, so that's plus 12.01, and that's going to give us 44.01 grams altogether. So 44.01 grams of CO2 for every 1 mole of CO2. Our molar masses are always going to be in grams per mole. Now I wrote grams on the bottom here because I want to be able to cancel out grams on the top. If I wrote grams on the top, it would be grams times grams, that'd be grams squared, big mess, and we want to get into moles. So we want our units to cancel top to bottom and guide us along to the end final unit. Okay, so right now we are in moles of CO2, and we want to keep going because we're not yet in our final unit, which we want, which is volume. So to go from moles of a gas at STP to volume of a gas, we have this really handy conversion. So only at STP, and only for gases, both of these are true here, so gas and STP, we know that 1 mole of any gas at STP, so 1 mole of CO2 at STP, is equal to or takes up 22.4 liters of space. So liters of CO2. And when we cancel all our units out, we'll see that we're left in liters, which is what we wanted. So our grams cancel out here and here. So remember, top to bottom, grams cancel. Moles of CO2 cancel here and here. And we're left with what we want, which is our liters of CO2. So when you plug this into your calculator really handily, you can just plug it in all at once. Type in 0.3 times 1 times 22.4, then hit divided by 44.01, and then hit divided by 1, or in this case, I mean, it doesn't matter because it's a 1, but this was another number. You'd hit divided by again, not multiply. So you should get 0.15 liters, and that would be the correct number of sig figs. We started with something with 3 sig figs. If you don't remember sig figs, see the link to a sig fig tutorial video in our School Loop folder. But this is the correct number of sig figs and our correct units. So we're here, 0.15 liters of CO2. Now, just a quick note, you can only use, so write this down for yourself for later when you're working on homework. So you can only use 22.4 liters per mole of gas at STP. If you have any other conditions other than STP, so remember that standard pressure is 1 atmosphere, 760 torr, and your standard temperature is going to be 0 degrees Celsius. If you have any other temperature or pressure, you have to use the ideal gas law. Okay, going to the next one. Finding the volume in liters of 0.3 grams of tin oxide. The density of tin oxide is 6.85 grams per cubic centimeter. Cubic centimeter is a volume, grams is a mass. This whole thing here, grams per cubic centimeter, that's going to be our units of our density in this case. So again, I'm always going to write down what I'm starting with. So 0.30 grams, SnO2. And I'm going to go from my grams to volume. So this part's a volume. So this is going to be really simple. The only thing I need to do here is use our density as a conversion factor. So we know that the density of SnO2 is 6.85 grams per cubic centimeter. Okay, so now I've canceled out my grams of my substance, and I'm left in cubic centimeters of it. So this tells me that I want my volume in liters, so I can't leave it in cubic centimeters. So I'm going to go ahead and convert that to liters. So 1 cubic centimeter is equal to 1 milliliter. This is worth memorizing. This is definitely something worth memorizing that will just help you out a lot later on. And I know that there are 1,000 milliliters in every liter. So my cancellations go like this. So my grams cancel out, cubic centimeters cancel, milliliters cancel, and I'm left in liters, which is great because that's what I want. So plugging all this into your calculator, so 0.3 times 1 times 1 times 1 divided by 6.85 divided by 1 divided by 1,000 equals, and I'm going to go ahead and write this one in scientific notation because it's quite small, 4.4 times 10 to the negative 5 liters. And I will go ahead and put a link to a scientific notation tutorial in our school loop as well if you need some brushing up on how to do scientific notation. Okay, so here we use density as a conversion factor. Okay, next problem. Find the volume of a solution, so these are all going to be volumes. 1.3 grams of calcium hydroxide is dissolved to form a 0.20 molar solution. Alright, so again, I'm always going to write down what I'm starting with. Now, in this case, I'm going to write down 0.30 grams of calcium hydroxide. So I want to find the volume of that solution, and not the 0.2 molars of solution, because, I wouldn't write anything there. So, 0.30 grams calcium hydroxide solution. And remembering that I can't go directly from grams to liters, I have to convert to moles first. So I'm going to go ahead and use my molar mass here, times. Now using the periodic table, I'm going to add up 2 oxygens, 2 hydrogens, and 1 calcium. This 2 carries to everything in the parentheses here. So 74.096 grams calcium hydroxide. And I'm keeping a lot more digits than I'm going to need in my final answer here, so I don't get rounding errors at the very end. And so that's for every 1 mole of calcium hydroxide. Okay, so now I'm in moles, and I'm not in a gas, I'm not at STP, so I can't use my same trick that I used up here. I can't use 22.4 liters per mole, because this isn't a gas. This is a solution. However, we do have a molarity. We know that this is 0.20 molar solution. Molar is this common symbol you'll see all year for solutions, and that means moles per liter. So we know that there are 0.20 moles for every 1 liter. So I'm going to use that as a conversion factor here. So the 0.2 is going to go with the moles, 0.2. So I'm going to put moles on the bottom so it cancels. So 0.20 moles of calcium hydroxide per every 1 liter. All right, plugging that into my calculator again, 0.3 times 1 times 1 divided by 74.096 divided by 0.2, you should get 0.020 liters with the correct number of sig figs. So in this case, my trick was, or my conversion factor, was that I used the definition of molarity to find volume of solution. I'm going back really quickly, showing you the cancellations. Grams canceled there, moles canceled there, and it left us in liters. Okay, last problem for number 3. Find the volume of 0.30 grams of SO2 gas at 30 degrees Celsius and 400 torr. So this is not a STP. So in this case, we could get this far and no further. So what I'm going to have to do, since this is a gas and this is not a STP, is use the ideal gas law. So the ideal gas law, if you have not memorized it, is on the back of your periodic table, and it is PV equals nRT So in this case, I'm going to find volume. So what I like to do is rearrange my equations before I plug anything in. So I'm going to rearrange this for volume. So that's going to give me volume. It's going to equal to nRT over P. All right, so what do all of these variables mean? V is volume. That's going to be in liters. Your N is the number of moles you have. That's, of course, in moles. R is going to be your constant, your ideal gas constant. T is going to be your temperature, and that's going to be in kelvins. And P is going to be your pressure, and that's going to be in atmospheres. So we're going to go ahead and plug all of this in here. So for N, for number of moles, I don't have number of moles, but I do have the number of grams. So this is going to take up a lot of space, so write kind of small if you can. Okay, so I can find my number of moles pretty easily. You can either do this off to the side or directly in the formula. It doesn't matter to me, whichever you're more comfortable with. So I'm just going to do it all in here to show you how. So 0.30 grams of our SO2. And I'm going to go ahead and convert that using molar mass to moles. So my 1 mole of SO2 is going to be equal to 64.06 grams of SO2. And again, that's my molar mass that I added up from the periodic table. So that takes care of the N. The R is our ideal gas constant. So that is on the back of your periodic table. So that's going to be given to you on the AP test. So 0.0821 when you look that up. Liters over atmospheres divided by moles times kelvins. Okay, so that's our constant that takes care of the R. The T is in temperature. It needs to be in kelvins. So we have 30 degrees Celsius plus 273. And so that's going to be kelvins here. So this is going to be kelvins. Sorry for that. So anytime you need to convert anything from Celsius to kelvins, add 273. Again, also in the back of your periodic table. Or you can subtract 273 from Kelvin to get back to Celsius. Divided by, so that takes care of our T, divided by our pressure. So our pressure is 400 torr. We can't put torr in here because this needs to be in atmospheres. We want our units to match up here to cancel out. So I'm going to convert this to atmospheres. You'll find on the back of your periodic table, so again, here's our gas constant we used right here. And here is our temperature conversion. So 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr. So 1 atmosphere is going to be equal to 760 torr. 760 torr, 1 atmosphere. Okay, so unit cancellations here. So our grams cancel here. I'm left in moles, which is what I want for my N. My R is going to cancel other things, so I'll show you that in a minute. Your Celsius is canceling out because you're converting it to kelvins, so you're in kelvins here. There's nothing to cross out, really, here. I guess this could be kelvins per 1 Celsius, and you'd cancel that out. But regardless, that's going to be Kelvin. And your torr cancels here. Your other units, because you want to end up in only volume, are going to cancel out thanks to your ideal gas constant. So atmospheres cancel atmospheres. Moles cancel moles. Kelvins cancel kelvins. You're left with liters, which is what you're going to want in the end. So when you plug all of this into your calculator, and I want you to make sure that you actually plug this one in, don't just copy mine down, because I want to make sure you can plug this in correctly and get the correct answer. It's going to be equal to 0.22 liters with the correct number of sig figs. So please take the time and plug that into your calculator. So since this was not at STP, must used ideal gas law. Okay, so that's probably the most complicated of those. Okay guys, so for number 4, we're going to find the density of all of these different samples that we already looked at in the previous problem. We're going to use values from problem 3 when needed. So that means that all these liters, all these volumes that we already calculated, we don't need to do that again. Okay, So first up is CO2 gas at STP at standard temperature and pressure. Notice we don't have a specific amount of CO2 that we're going to calculate the density for. It doesn't matter. The density of CO2 at STP is the density of CO2 at STP. It doesn't matter how much of it we have. Okay, so we do know, however, that the molar mass of CO2 is 44.01 grams of CO2 per every 1 mole of CO2. And we know that this is at STP, so this is going to be very easy. So we need to be in grams per liter, and so we already have grams on the top, but we just need to get liters on the bottom and cancel moles. But because this is at STP and it's a gas, we can use that conversion factor again, that 22.4 liters. So we know that 1 mole of CO2 gas takes up 22.4 liters of space at STP. And so our units here work out. Moles cancel here, moles cancel there, and we're in grams per liter, which is what we wanted. So now you can go ahead and plug this into your calculator, and you should get, let's see, 1.96 grams per liter for your density. Okay, next one, tin oxide, our solid. So we know that the 6.85 grams, so if we look back up here, we know that the density is 6.85 grams per cubic centimeter, so we're actually almost there. We already have the density, we just need to do some unit conversions. So looking back, we knew from our previous problem that the density is 6.85 grams per cubic centimeter. So we're almost there, we just need to be in grams per liter. So the only thing we need to do is convert this cubic centimeters down here to liters. So we know that there is 1 cubic centimeter in every 1 milliliter. And we also know that there are 1,000 milliliters in 1 liter. So our units work out like this. So we have cubic centimeters canceled, milliliters canceled. We have grams per liter, which is what we want. And again, we just got that density from the previous problem, so we didn't have to do anything special to get it. We just had to convert cubic centimeters to liters. So plugging all that into your calculator, you should have 6,850 grams per liter. Okay, moving on to our next one. 0.020 molar calcium hydroxide. So we know that the mass of calcium hydroxide is 0.30 grams. So mass is 0.30 grams. So how do we know that? Well, from our previous problem here, 0.30 grams. So we know that the mass is 0.30 grams. And so for the mass of H2O, we are going to go ahead and start with the volume of H2O, which we figured out from above. We figured out that the volume of the total solution was 0.20 liters up here in the problem, in problem 3. So we're going to go ahead and start with that. So 0.020 liters. Now, the instructions up here tell us for aqueous solutions, which we're dealing with here, assume the volume of solutes, that is, the volume of calcium hydroxide, is negligible, so it doesn't matter. So that whole volume here we're going to assume is water. And then we're going to assume the density of water is 1 gram per milliliter. So what I need to do first is get out of liters to get into milliliters. So eventually I want to change this to grams using this. So I'm going to go ahead and multiply this. So I know that there are 1,000 milliliters in every 1 liter. My liters are going to cancel. And I'm instructed to use the density of water as 1.0 gram per milliliter for my instructions here. So 1.0 from the top, so 1 gram per 1 milliliter. So my units canceling look like this. So liters, milliliters, I'm left in grams, which is what I want. So then I found that my mass of the water is 20 grams. So my mass of my solute is 0.3 grams. My mass of my water is 20 grams. So to get density from this, density equals mass over volume, you'll remember. So my mass is going to be my total mass. So it's going to be 0.3 plus 20. So that's going to be 20.3 0.30 grams divided by my volume, which I started with here, which I already had. My volume is going to be 0.020 liters, so we're in grams per liter. Just dividing that in your calculator, you should get 1,020 grams per liter. So that's your density of your aqueous solution of calcium hydroxide. Lastly, sulfur dioxide, gas at 30 degrees Celsius and 400 torr. Well, here, so again, my density is going to be mass over volume. I already calculated my volume in the problem above, 0.22 liters. And I know that I have 30 grams of it also from this problem above, so I have 30 grams. So I have grams, I have liters, all I need to do is divide. So this one's turning out to be quite simple, 0.30 grams from the problem above, and 0.22 liters. So that's grams per liter, no cancellations needed here. When you plug this in, 1.4 grams per liter is your answer. Okay, so those are all of our densities for our samples. So it says compare these calculated densities to your particulate diagrams in question 1 and predictions in question 2. Okay, so let's go ahead and take a look at question 1 again. So part 1. Here was our part 1. And so we said that SO2 was the least dense. So let's go ahead and take a look at our densities. So SO2 was the least dense. So let's see, let's find SO2. Is it? Yes, it's only 1.4 grams per liter. Followed by CO2, and CO2 is 1.96. That's the next dense. Followed by calcium hydroxide, which, yes, that is the next one. And then the most dense, of course, being our tin oxide here. So we were correct in our predictions, and our math backs us up on that. Okay, question 5 is just for you. State a few things you need to remember or review, or that you learned something new in questions 1 through 4. So this is a good spot for you to go ahead and reflect. Go ahead and jot down any questions that you have, and thank you for watching. We'll see you next time.